asked to do this yesterday, and I almost pleaded. I was like, please, please, please. So Luke started here in 2011 from Kingston, Jamaica, and I actually started in 2013, but we basically had the exact same experience here, Lawrence. Luke has taken 5 classes with me, and in that only 2 years' time, I have seen Luke go from a more of a timid student to a chemist problem solver. And it's fantastic how much he approaches these problems and can solve them rather quickly, because he's actually in negotiations at the moment, I think, with the World Bank Group, who's looking for someone to help them solve problems in establishing developing countries' financial crises and such. And so Luke is the problem solver, and we really, really want him. Before that, he's going to tell you ways to problem solve, or maybe commercially biofuel produce use of nano-sized mixed oxides. So, anyway, Luke.
Oh, there are a lot of people here. Okay. Hi, my name is Luke Phillips, and today I'm going to be talking about using nano-sized mixed oxide catalysts in the commercial production of biofuels. So, before I start, like a little bit of background. So most people, if you're like me, like when you're small and think about chemistry, you're just like, oh cool, mad scientist in the lab, puts a lot of things together, and cool things happen. It's cool for like a 7-year-old kid. Lots and lots of explosions. So lots of reactions produce basically tons of energy, and that's what these explosions come from. But one reaction in particular that humans have harnessed to use humans have harnessed to our great benefit is the combustion reaction. So in the combustion reaction, we burn hydrocarbons to get water and oxygen. Water and carbon dioxide. So the black dots are our carbon molecules, and our red dots are oxygens, and our white dots are hydrogen. So here we have methane, which is our hydrocarbon, and we add oxygen, and we get, boom, carbon dioxide and water. So how do we harness these combustion reactions in, I guess, our everyday technology? Any guesses? Here's a hint. So use fuel. Well, what are fuels? So fuel is any substance that produces useful work energy when it undergoes a chemical reaction. So current examples of fuels, well, we have coal, oil, and petrol, just to name a few. So what's the difference between fuels and biofuels? Well, biofuels are just fuels that we get through a process called biomass conversion. So why do we care about biofuels? Well, they're renewable, first of all, which means they're a lot nicer to us. They will be cheaper, and they're more easily obtained. So instead of going into a mine and using TNT to blast like 1,000,000 holes and having cave-ins and landslides and getting stuck in crises, or getting stuck in an oil rig and an oil spill to fracking and stuff like that, we get nice biofuels that we can grow on a farm and ferment to get bioethanol. So what is this biomass conversion process? So here's an example. Basically, we start with a feedstock, which is our, I guess, starting product initially. An example of that would be like here, sugar cane, or I guess for Americans, corn is a better example, or wood or other stuff. And then some, but not all feedstocks have to go through like a pre-processing process, which is like for wood chips, where they're dense, crushed together, or for like more complex, I guess, cellulose or sugar compounds are broken down into glucose, so they can be ready for conversion. And our conversion processes is what we do to our now pre-processed feedstock to get our primary energy product. So an example of a conversion process would be fermentation in the case of simple sugars, alcohol, or transesterification. So we get biodiesel, or anaerobic respiration in terms of natural gas. And then we have our primary energy product produced, which are biodiesel, and our bioethanol, and our biocoal, and other stuff. Yeah, so the moral of the story, corn is good for you. So what do we use biofuels for? Well, basically, they can be used for anything that we use normal fuels for. We can have a biodiesel substitute, we have bioethanol, so motor vehicles and other such engines, but can also use bioethanol in particular, because it's small, for synthesis and conversion into other intermediates or biofuels, such as butanol. So this is what the main focus of my talk today. So why am I interested in more complex carbon chains, or butanol in particular? Well, first of all, longer carbon chains means that more energy is produced through that combustion reaction. So, well, and because of that, butanol has a more similar structure to carbon, so it can be added directly to gasoline, or we have less modification to our engines in order to implement butanol in as a primary energy product or fuel. So, I was going to make a joke, but everything about cars became corny. Current methods of converting to more advanced, I guess, climate change. So, for those who are non-chemists, so this is bioethanol, and this is ethene, biofuel. So, how do we get to bioethanol? Well, we go through basically an alkyl condensation process. So, for those of you who haven't had organic chemistry yet, this is and this are the same thing. So, these ends right here are carbons, and then this is just our OH bond. The hydrogens on the carbons aren't drawn here because they're not really that important. So, we can go through here and we have sort of a reduction happening, in which we get two of these little ketone molecules, and then we have an alkyl condensation, we get this, and then we go here, and I get our butanol. That's the important step. But how do we actually get it industrially right now? Well, we get most of our butanol from petrochemical feedstock of propylene. So propylene is a byproduct of the fracking process, and what we do is take that propylene, and with carbon dioxide and water, we use a rhodium catalyst to get to our butylaldehyde, or make this fluorocarbon chain. And then we add hydrogen to get our alcohol of choice, butanol or isobutanol. So what's the problem with this? Well, as you can see, some of these products aren't very efficient, and we can't really use ethanol because it would require more modification to our current system. And very efficient catalysts can be expensive. So pure rhodium costs about $13,000 US for 100 grams. That's pretty expensive, at least by my standards. So I've been talking about catalysts and whatnot. So what is a catalyst? So a catalyst is a substance that increases the rate of a reaction without actually partaking in the reaction itself. So how it does this, it lowers the activation energy of the reaction. So what is activation energy? Well, so here's an energy level diagram. Our reactants here have a certain amount of internal energy. We add energy to overcome this activation energy. So here we go, and then from here we have our reaction starting, and we produce our products way down here. So the useful energy that we get is from the difference between the internal energy of our products here and our reactants right there. And this is the difference between using catalyst and not using catalyst. So when we add a catalyst, we require to put in less energy into the reaction to obtain our products. That's the basis of it. So examples of normal catalysts are transition metals or transition metal oxides and enzymes. So an example that's closer to home, I'm betting most people are familiar with hydrogen peroxide or have it in their homes, medicine cabinets, kitchens. And I bet most people have been cut. So what happens is our blood has an enzyme called catalase, and when it comes in contact with hydrogen peroxide, it increases the rate of the reaction that breaks up hydrogen peroxide into water and oxygen. See? Lots of bubbles. So how do catalysts work? Well, for enzymes, I have no idea. Not a biochemist, no idea. But mixed oxides, well, they take advantage of what's properly called absorption. So it increases the number of collisions that occur by adsorbing chemicals to the surface of the catalyst. So what does that mean exactly? Adsorption. So here's a little example. So this is our catalyst, and these are our molecules. So there are two main types of adsorption. There's chemisorption and physisorption. In chemisorption, there's a chemical reaction that occurs that causes our molecule to stick to the surface of our catalyst. And in physisorption, there's more of a physical binding, such as van der Waals forces, or random forces that just hold the molecule in place. And after the reaction occurs, then it's free to go on its way to make room for more. More clear example of this, we have our true reactive elements here, and then it's bound to the surface of our reactions. Laser point. Hydrogen bound, and then our ethene bound. Now they're a lot closer to each other, so the chances of collision happening are a lot more likely. One collision, two collision, then we get our desorbed final product. So mixed oxides, what are they? So mixed oxide is a compound that contains two or more cations and a single oxide anion. What is a cation? Well, a cation is a positively charged atom, such as our potassium right here, but donated by this little plus. And an anion example is our chlorine, which just has the minus sign over there. So how does this relate to our mixed oxides? Well, let's see. So this is an example of the mixed oxide in question. So we have our zirconium, or zinc, and our oxide. So what are the cations and the anions? Well, we have our cations here, 4 pluses, and anion is over here. Oh, forgot to mention, these X and little y's are just denoting the ratio of each atoms in the compound. So think of, say, a water molecule. So you have H2O, so this Y would be the little 2 in that chemical formula. So what are some of the properties in the oxides? Well, we're talking about nanoparticles, so the nanosized means they can be really tiny. So even though they're really tiny, though, they're porous and they have a large surface area, which makes them really good for this adsorption process, okay? Making good catalysts. And they can be used to create 2 separate environments for this reaction. Really get into what do I mean by this? So here's an example. This is an electromicrograph of our mixed oxide catalyst. So as you can see, there are a lot of ridges and grooves. This is 50 nanometers, and this is really zoomed in. You can see all these grooves and troughs and, I guess, bunches that separate into, I guess, different containers. Or it makes the substance not flat, so we have like a lot of space for things to absorb to. So this contributes to our like large surface area properties. And we can manipulate the surface area of our mixed oxide to create different acid and base sites. So what do I mean by that? Well, first let me explain what an acid is. So what is an acid? There are really 2 main types. We have the Lewis acid, which is an electron pair acceptor, and a Brown's acid, which is a proton donor. And likewise, we have Lewis base is an electron pair donor, and the Bronsted base is a proton acceptor. So what we're interested in is the acid-catalyzed reactions. So this is an example of an acid-catalyzed reaction. You have our proton that's been donated here, and these 2 dots represent our lone pair, and they're like, oh, cool, positive charge. Let's be friends. And then you have our reaction over here. Our final product over here. So now that we've got a little bit of background information, let's get into the paper that sparked this whole topic. So this is a paper on using mixed oxides, or the direct conversion of biomethanol to isobutene using nanosized zinc zirconium oxide mixed oxides with balanced acid and base sites. So just a roadmap of our experiment. First is synthesize the mixed oxides, determine the surface area, attempt the bioethanol to isobutene conversion, and then check if it worked. So let's start with our synthesis. So how do we synthesize this? First we started with our zirconium and zinc oxides, and we dissolved them in water, and then sonicated that mixture. What does sonicated mean? Basically, our mixture was blasted with high frequency sound waves until there was a homogeneous. And then we took that mixture and added 25 grams of carbon black, which is next another really porous high surface area solid, and then calcine at 400 degrees Celsius. What that means is it was basically just heated until all the moisture is evaporated off. And then the temperature was ramped up and held at 550 degrees Celsius and held for about 20 hours. This was done just to see if there was any degradation of our catalyst that would happen if exposed to high temperatures for a long time. So now we need to determine surface area. So this looks really confusing, but on the y-axis we have our volume of gas and our relative pressure on the x-axis. So what we did to determine the surface area, we basically had a container, we put our catalyst in and filled it with nitrogen gas, and then we see what stuck. So the length of, the height of these gas basically represent the volume of gas that was adsorbed to the surface of a different oxide. So we can see here our zirconium oxide has the tallest graph, just from eyeballing it, and our zinc had the smallest one. So intuitively, it kind of tells us that with a higher ratio of zirconium to zinc, our mixed oxide would have a higher surface area. And then it's confirmed through this representation. So as you can see here, on our only zirconium one, we've got like whopping 138 meters squared per gram, and then our 1 to 10, as we thought, zinc zirconium has 124 meters squared per gram of zinc absorbed, gas absorbed. So meters squared per gram, let's think about that. Like a gram is like this much of mixed oxide. So that's pretty high surface area. So now that we've synthesized, I guess, and confirmed the surface area of our catalyst, let's attempt conversion. So how was this reaction carried out? So we had this took place in stainless steel reactors because, well, it had to get really hot. So what we did, we took 100 milligrams of our synthesized mixed oxide mixed with some silicon carbide and sandwiched it between quartz wool. And then there was also a thermocouple placed within the catalyst bed just to monitor how the reaction changed with temperature. And so our reactants were then fed into the stainless steel reactor by an evaporator carried by nitrogen gas. And then we identified or characterized our products using different characterization techniques such as gas chromatography and FID before getting a cold trap and further analysis. So what happens on these catalysts by themselves and why do we need the mixed oxide? So this is an example of the reaction that occurs on zinc oxide. So we start off with our bioethanol, and again, it's reduced. Then we have our aldol condensation happening, which for you non-organic chemists, again, this means we form our 4-carbon bond chain. Then again, we reduce it, which means we get rid of the hydrogen right there. And then we get this molecule, which decomposes to give us acetone and formic acid. And this goes off to give us carbon dioxide H2O. So as you can see, no isobutene. Alright, then what happens when we try it on zirconium? That might be better. No, we just get our ethanol, then decompose to ethene and water. But when you put them together, I like to see, it's magic. So we have our ethanol here, it goes through the same reaction that happened on our zinc catalyst. So we go through our reduction, condensation, reduction, and then we get down to our acetone and formic acid. So instead of going this way, because of our zirconium catalyst now have acid environment, so we get protonization. So we get this sort of acetone derivative product, and that can undergo dehydration to propene, or we can go condensation, have two of these come together to make this big molecule right here. And this molecule decomposes or simply breaks up to give us what we want. Our isobutene, really important right here, and our acetone, CO2 and H2O. So this is a proposed reaction mechanism. Did our reaction work? Did we get what we want? So this is our results slide. On the left, we have our conversion percentage and our selectivity. So a lot of our bioethanol was converted. And over on the right, I just want to point out really important, the major products are acetone, are the yellow bars. Isobutene is our aquamarine-ish color. I don't know, I'm not a color person. And carbon dioxide is in blue. So as you can see here, like we thought, on the x-axis we have a ratio of zinc to zirconium. So we have a 1 to 10, which is zinc to zirconium ratio. And as we can see, as we thought, we've got a lot of isobutene production. And then to reduce that ratio, the amount of zirconium to zinc, we have less isobutene production. And a 1 to 1, then like less than 20% of bioethanol is converted to isobutene. So this tells us that our best catalyst, or most efficient ratio, would be a more acidic of 1 to 10, zinc to zirconium oxide. Now that we have our efficient catalyst, how does temperature affect this reaction? Since we have a thermocouple, see, because everything's temperature dependent. So we start off at 400 degrees Celsius. Again, on our x-axis or y-axis, we have conversion and the selectivity, and the temperature on our x-axis. Same colors correspond to the same products. So as you can see, at 400 degrees Celsius, our acetone is the major product, which is like more than 50% of the bioethanol we tried to convert was acetone. But then when we go up, ramp the temperature to about 450 degrees, our isobutene becomes the major product of the reaction. Why this happens, I'm not exactly sure at this point. But then after further increase of the temperature, we see less and less isobutene and an increase in our carbon dioxide concentration. So what we've confirmed from this experiment is that it is possible to efficiently synthesize isobutene using mixed oxide catalyst. You just saw the reaction with our 1-gen catalyst at 450 degrees Celsius. There was an 80% conversion to isobutene, which is pretty cool. temperature definitely affects our reaction yield. And lastly, success requires a more acidic environment for the reaction to take place as proceeded. So what are some other uses of this product? Well, I was reading a few weeks ago and I came across another cool paper that used a similar method to upgrade biofuel and upgrading bio oil. It's pretty cool. You should check it out. But yeah, and I'd like to thank the Untitled Chapter department for allowing me to conduct research, and Dave Hall for helping prepare this talk, especially. And any questions?
Question. So the table that you had with the pore size and the absorption surface area. Where did you go? So you said the higher surface area was more important, or is it better outcome? Better outcome. But the pore size looks like it's much better for the lower. So you have 62 nanometer pore size versus 21 nanometer pore size. And so would it be better in some cases, maybe if you weren't using this for absorption of the, was it ethene that you were using it for absorption? Would it be better to have a different ratio if you were trying to get different compounds to absorb to the surface?
I mean, that's a possibility. Depends on, I guess, the size of the molecule you want to absorb. So,
okay.
I was thinking that depending on, I guess, what exactly you are trying to, I guess, react, then pore size could come into play. Or it would be better if there was a larger pore size as opposed to like more constricting one.
And are you saying in this particular one, is it more of a chemisorption or a physisorption that's important?
It's more of a physisorption, I think, at least from reading the paper. That's what I got from it.
So you said you had to heat it to 400 degrees to drive the moisture off. Well, if water comes off at 100 C, why do you have to go to 400 C?
Well,
just curious.
I mean, well, I think it's just more just to ensure dryness because there are also there's also like nitrites in the compound. So just to make sure that all we had left at this point was our zirconium and zinc oxides. Any more questions?
So I guess I have one more. It's totally unrelated to what I just asked. So at the beginning you said corn is good for you. Do you have any sense of, I know there's, since where you're headed next is how biofuels might be helpful, right? If I'm understanding correctly. Do you have any sense of one of the things that we always like to think about in environmental is unintended consequences of using biotechnologies? And corn actually has caused some of those. Do you have any sense of those?
I personally don't have a great sense of that. Just because I wasn't really looking at corn, I just thought corn would be more relatable to like everyone here.
Just curious.
Because well, I was thinking of Jamaica and like use of biofuels because we don't have oil, but we have sugarcane, lots of it thanks to Europeans. So we process what we don't eat and turn it into biofuel. But I don't.
So I just know that like they put palm to do biofuels, and they ended up in kind of Malaysia, and they ended up taking up all those wetlands that actually increased the carbon that was being released because they took all those palm trees out.
Yeah.
And they also say that some of the corn things can be related to some shortages of corn and this peak in corn prices that caused some famine stuff. So it's a very interesting, very interrelated issue.
How much energy is used in this reaction? Because if you're using fuels to get this energy or get this reaction to actually go to completion,
lots of high temperatures.
Then doesn't that kind of defeat the purpose?
Kind of, but I guess the main thing is that these catalysts that we have are like not less expensive, first of all, and they last for a long time. So once you've synthesized once, you don't really need to make like unless you're making from new product. You don't need to buy it one time, basically. Keep reusing.
What's that you're speaking one more time?